Hey everyone, welcome back to another video, and we will do a continuation of the previous series which we solved with variation of parameters, but now we will solve higher order non-homogeneous differential equations. And without further ado, let's go to our first example. Hi everyone, this is our example of solving non-homogeneous differential equations. And so, to start with, we're gonna write down the superposition principle as usual, which is yc plus yp, denote this with equation 1. Solving for the homogeneous part, which is pretty straightforward. Factoring the r, we get here 3 solutions because we're dealing with a cubic polynomial. And so our yc will be c1 times e to the 0, which is 1, plus c2 times e to the 1 times t is t, and c3 e to the negative 1 times t is just negative t, and denote this with equation 2. And so we've solved for the homogeneous part. Now let's solve for the non-homogeneous part. And before solving it, see here that we're going to use this formula. Our yp is equals to u times y1 plus v times y2 plus w times y3. And so we're gonna use this formula of our u, v, and also we're missing a w here for our to plug in to our particular solution to the non-homogeneous part, which is stated in the above. And so without further ado, let's first state our y1, which is just 1 e to the 0, our y2 e of t, and our y3, which is just e to the negative t. And so we're gonna need our Wronskian for our differential equation here, and we're gonna have a 3 by 3 determinant, which is 1 0 0 e to the t, e to the t, e to the t, the first derivative and second derivative, I forgot to mention that. E to the negative t, first derivative is e to the negative e to the negative t, and second derivative is just e to the negative t. And taking the Wronskian of this, we can just take from the first column because we have 2 zeros here, and it's pretty convenient because we don't need to calculate the other 2 determinants. And so we're just left with 1 times the determinant of e to the t times e to the negative t, e to the t, e to the negative t. And so we have here e to the t times e to the negative t, which is just e to the 0, 1, minus e to the negative t times e to the t is 0, times e to the 0 is 1, times negative 1 is negative 1. So we get here 2 for our Wronskian. So we have our y1, y2, y3, and our Wronskian towards our differential equations. And now let's calculate for our Wronskian for u prime, v prime, and w prime. And before we start any confusions, let's write down a system of equations that will represent for our u prime, v prime, and w prime. And so our u prime times y1 plus v prime times y2 plus w prime times y3, everything is equal to 0. U prime times y1 prime plus v prime times y2 prime plus w prime times y3 prime equals to 0. And lastly is u prime times y1 double prime plus v prime times y2 double prime plus w prime times y3 double prime, which is equals f of t, or if you remember it as g of t, the non-homogeneous part of our equation, which is 9 of t here. So we have a system of equations here that will be represented as a matrix, and we will calculate the determinant of a 3 by 3 matrix. As you can see, we have 3 coefficients here, which is just u prime, v prime, w prime. And so by doing that, or actually we have coefficients here of y1, y2, no, u prime, v prime, and w prime. So by doing that, let's calculate for our first Wronskian, which is for our u prime here, the 3 by 3 determinant of 1 e to the t, e to the negative t. You all may be wondering what's 1 here, why actually this is not 1, this is 9 of t. You all may be wondering why I didn't put 1 here instead of 9 of t, because we have a 1 in our Wronskian right here. It's because every time you want to calculate for let's say you want to calculate for u prime, you substitute the column for u prime here, which is the first column right here, with the coefficients of the nonlinear part, which is g of t. And if you want to calculate for v prime, for the Wronskian of v prime right here, you would want to substitute the second column here, or e of t, with g of t, which is 90. And you all will see in the next few steps, because right now maybe it's confusing for you all, but it will not in a few minutes, I promise. So we know that everything here is just 0, and taking the first derivative, which we know this e of t, and we know for a fact this is e to the negative t. And then before calculating the determinant, let's take the Wronskian. Also, let's write down the Wronskian for v prime. And so this stays 1, 0, 0 as our original Wronskian right here. And so we're gonna substitute our e of t with 90, and this is just 0, 0, and e to the negative t, and this is just as our original Wronskian. And then let's also do it for our w prime, the Wronskian for w prime. And this is just 1, 0, 0 as our original Wronskian. This also as our original Wronskian. And this is, we substitute the value of e to the negative t with 90, 0, and 0. And so you have 3 Wronskians here. And as you may see, that the Wronskian of v prime and w prime is just 0, because if you take the first column for both, and we use the method of closing the first row and first column here and calculate for 0 times e to the negative t minus 0 times negative e to the negative t, which is 0 minus 0 is 0 times 1, our coefficients here, which is just 1 times 0 is 0. And so it also works for this part, which is just 0. So we can conclude for both of this Wronskian. Particularly for this problem, it's pretty simple because we got 0 for both Wronskians, but it is also not that hard, even though you're not getting 0 for both Wronskians, because you will just need to calculate for the determinant of it. A 3x3 matrix determinant is not that difficult. So calculate for our first Wronskian for our u prime here. Let's use the first row because we got two zeros here and it's pretty convenient. And so by doing it, we will get 90 times the determinant of e to the t, negative e to the negative t, e to the t, e to the negative t. And we don't need to write down both of the determinants in the next part, because 0 times the determinant is just 0. And so we have here 90 times e to the t times e to the negative t is just e to the 0, 1 minus negative 1. And so we will get here 18t. And so we have all values for our Wronskian values for u prime, v prime, and w prime. And let's sub all of our values here to our 3 equations that we have here, or 3 integrals that we have here. But rest assured that we don't need to use the v and w equations, because we know the integration of 0 is just 0. So we just need to calculate for u. And so we have here u is equals to the Wronskian of u prime, which is just 18t, just double checking, divided by the Wronskian of the differential equation, which is just 2, multiply everything by dt, and we will get here 9 over 2t squared. And so substituting this back to our yp that we state at the start of the problem here for our solution to the non-homogeneous part, and substituting our yp back to our superposition principle with our solution to the homogeneous part, we will get y equals to yc. Remember, our yc is c, our second equation here, c1 plus c2 e to the t, c2 e to the t plus c3 e to the negative t, plus our yp, or our solution to the non-homogeneous part, which we will just need the u and y1, and our y1 is fortunately 1, so 1 times u, or 1 times 9 over 2t squared is just 9 over 2t squared. And so this is our final solution, or we're gonna say this is our general solution to this higher order differential equation.